Hello everyone. Welcome back. In today's lecture, we'll discuss cable anchoring and grouting, two important ground improvement techniques widely used in civil engineering. These methods help stabilize weak soil and rock, making construction safer for bridges, retaining walls, tunnels, dams, and deep excavations. By the end of this lecture, you'll understand their working principles, construction process, applications, and different grouting methods. Let's begin with the basic concept of cable anchoring. Cable anchoring is a technique used to transfer loads from unstable soil or rock to a deeper, stronger layer using high-strength steel cables, also called tendons. Instead of resisting earth pressure with thick concrete walls, engineers use tensioned cables to provide support. Imagine securing a tent using ropes attached to pegs driven into the ground. The ropes prevent the tent from moving. Similarly, cable anchors keep retaining walls, cofferdams, and rock slopes stable by resisting the pressure exerted by soil and water. Now let's understand how cable anchoring actually works. A hole is first drilled into the ground until it reaches competent rock or dense soil. A steel cable is inserted into this hole, and its far end is fixed securely inside the strong ground. The outer end is then tensioned using hydraulic jacks and anchored to the structure. This tensile force prevents the retaining wall or cofferdam from moving under earth and water pressure. Three common stabilization techniques are rock bolting, rock anchoring, and shotcreting. While rock bolts provide local support, cable anchors can resist much larger loads over longer distances. Cable anchors are classified into two types. The first is the temporary anchor, which provides support only during construction and is removed after the permanent structure becomes stable. The second is the permanent anchor, which remains within the structure throughout its service life and is protected against corrosion. Cable anchoring is widely used in deep basement excavations, bridge abutments, cofferdams, dam foundations, tunnel portals, and rock slopes. A good example is metro rail construction, where anchored retaining walls safely support deep excavations in densely populated cities. This visual illustrates the components involved in cable anchoring, including the anchor head, protective sheaths, and the grouted section that secures the tendon into the soil or rock. Now let's understand the construction sequence of cable anchoring. The process begins by drilling a hole to the required depth and inclination, usually using a percussion drilling machine. The steel tendons are then fabricated according to the design specifications and carefully lowered into the drilled hole, keeping them about 300 millimeters above the bottom. Next, cement grout is injected under a pressure of approximately 30 kilograms per square centimeter to fill the entire hole. After the grout has gained sufficient strength through curing, hydraulic jacks are used to tension or stress the cable. Finally, the anchor is locked in place to provide long-term support to the structure. Let's now discuss grouting, which is one of the most important steps in cable anchoring. Grouting is the process of filling the space around the anchor cable with a mixture of ordinary Portland cement and water. After grouting, sufficient curing time is provided before stressing the anchor, so that the grout develops the required strength. Grouting performs several important functions. It firmly bonds the steel cable to the surrounding soil or rock, protects the steel from corrosion, increases the load-carrying capacity of the anchor, and fills any voids that may allow groundwater seepage. In simple words, grout acts like a strong adhesive that firmly locks the anchor into the ground. Different soil conditions require different grouting methods. The 5 commonly used techniques are permeation grouting, compaction grouting, fracture grouting, chemical grouting, and jet grouting. Each method has a unique working principle and application. Engineers select the appropriate method based on factors such as soil type, groundwater level, required strength, and project requirements. Understanding these methods helps engineers improve weak ground conditions and ensure safe and durable foundations. The first method is permeation grouting. In this technique, a low-viscosity cement slurry or chemical grout is injected into the natural pores of sandy or gravelly soils without disturbing the soil structure. The grout flows through the interconnected voids, hardens over time, and binds the soil particles together. This process increases the strength of the soil while significantly reducing its permeability. Permeation grouting is widely used beneath bridge foundations, dam foundations, and tunnel projects where groundwater seepage needs to be controlled without causing any disturbance to the existing ground. The next method is compaction grouting. Unlike permeation grouting, this technique uses a very stiff cement grout injected under high pressure. Instead of entering the soil pores, the grout forms a compact bulb that pushes the surrounding soil outward. This action increases the density of the surrounding ground and improves its bearing capacity. Compaction grouting is commonly used beneath existing buildings, bridge foundations, and industrial structures to reduce settlement and strengthen loose sandy soils. One major advantage is that it improves the ground without the need to excavate or disturb the existing structure. Now let's discuss fracture grouting, which is also known as hydraulic fracturing. In this method, grout is injected into the ground at a pressure high enough to create small fractures in weak soil or rock. The grout then fills these fractures and hardens, forming a stronger and more stable ground mass. Unlike permeation grouting, which fills existing pores, fracture grouting creates new pathways for the grout. This technique is commonly used to stabilize embankments, rock foundations, and dam structures, especially where the soil has low permeability and ordinary grout cannot penetrate effectively. The fourth method is chemical grouting. Instead of using ordinary cement grout, engineers inject chemical solutions such as sodium silicate or polyurethane resins into the ground. These chemicals react after injection and form a gel-like material that binds soil particles together while making the ground waterproof. Chemical grouting is particularly effective in fine sands and silts, where cement particles are too large to penetrate the soil pores. It is widely used in underground metro tunnels, basement excavations, and water-retaining structures to reduce seepage and improve ground stability. The final grouting technique is jet grouting, one of the most versatile ground improvement methods used today. In this method, high-pressure jets of cement slurry are injected through a rotating drill rod. The powerful jet cuts the surrounding soil and mixes it with the grout, creating strong cylindrical columns called soilcrete columns. Depending on the construction method, jet grouting is classified into single, double, and triple jet grouting. Since it is effective in almost all soil types, jet grouting is widely used for deep excavations, tunnel construction, bridge foundations, and strengthening existing foundations in congested urban areas. Let's conclude today's lecture by reviewing the major advantages of cable anchoring and grouting. These techniques significantly improve the stability of excavations, retaining walls, slopes, and foundations. They reduce lateral movement, increase load-carrying capacity, and often provide a faster and more economical solution than constructing massive concrete retaining structures. Another important advantage is that they can be used effectively in both soil and rock conditions. With proper grouting and corrosion protection, cable anchors can provide reliable long-term performance. To summarize, cable anchoring provides the tensile resistance needed to stabilize the ground, while grouting ensures strong bonding, corrosion protection, and efficient load transfer. Together, they have become indispensable techniques in modern foundation and geotechnical engineering, contributing to the safe construction of bridges, tunnels, dams, retaining walls, and deep underground structures. Thank you for watching.